All right, this next unit is on acids and bases, particular types of substances. Usually we're dealing with solutions of these substances. We're going to start with the observable properties of acids and bases. So take some substance, dissolve it in water. If it's an acid, it has certain properties. If it's a base, it has certain properties. So we'll start with taste. If you were to taste an acid, though I would not recommend tasting any of the acids that we use in the laboratory, but if you were to taste something that was acidic, it would taste sour. And if you were to taste something that was basic, basic, that would taste bitter. So any foods or drinks that are sour, they're sour because of some acid. Any foods or drinks that are bitter taste that way because they are basic. What if you were to touch a solution of an acid or a solution of a base? Though again, not recommended, but sometimes chemicals spill and we get some stuff on our hands. What would it feel like if you were to touch an acid? So let's say we have a dilute solution of an acid. So I'm not talking about concentrated acid that's going to burn your skin, but a dilute solution, say you have 0.1 molar hydrochloric acid. What would that feel like? So the best way to describe what that would feel like is it would feel just like water. It has the same kind of texture and feel of water. Bases, that's not the case. You'll know that you have spilled base if you touch that spill and rub your fingers together and it feels slippery. That means that is a base. All right, reactions with metals. Acids, you can put yes, they do react with metals. And in that reaction between a metal, say magnesium metal, and an acid produces among the two products hydrochloric acid, or sorry, hydrogen gas. So magnesium and hydrochloric acid, for example, would produce hydrogen gas. We saw this reaction actually in the molar volume of a gas lab. That's the exact reaction that occurred there. As for bases reacting with metals, no, they don't. So let's put, maybe we'll be more specific, not just no. We'll do no reaction. All right, conductivity. In order for a solution to conduct electricity, we've seen this before, that solution needs to contain ions. So solutions of acids do contain ions, and we're going to say that some acids are fair conductors of electricity, and some are excellent conductors of electricity. We'll talk a little bit more about that later. Bases, same thing. Some bases are so-so conductors of electricity, and some are excellent conductors of electricity. Be thinking about what would determine the difference between a fair conductor of electricity and an excellent conductor of electricity. All right, next up we have indicators. Maybe make a note. Indicators are chemicals that are different colors in an acid or a base. Or technically they're different colors at different pHs. We haven't learned about pH yet. We'll learn about that later. But these chemicals are a certain color at one pH and a different color at a different pH. A couple that are important for this class are litmus and that second one there, phenol. The second pH is silent. We pronounce that phenolphthalein. Phenolphthalein. And that's the indicator that we'll use in our experiment. Litmus in the presence of an acid is red. And in the presence of a base, it is blue. Phenolphthalein in the presence of an acid is colorless. And in the presence of a base, it is pink. All right, on to different definitions. So different substances fit different definitions of acids and bases. The first one here is known as the Arrhenius definition. According to the Arrhenius definition, an acid is a substance that, when dissolved in water, forms hydrogen ions or hydronium ions. So H3O plus is called hydronium. What is the difference between a hydrogen ion and a hydronium ion? If you said water, you would be correct. So a hydronium ion is just take that H plus ion, add it to a water molecule, and you get H3O plus, called hydronium. So any substance that, you know what, I'm going to change the definition a little bit. So this will be important for later on. A substance that increases the concentration of hydrogen ions or hydronium ions in solution is considered an acid according to the Arrhenius definition. Base is any substance that when dissolved in water increases the concentration of hydroxide ions. So any substance that produces hydroxide ions in solution is a base according to the Arrhenius definition. So let's take a look at some examples. I'm going to write what are called ionization equations, or at least for the acid, and a dissociation equation for a base. So let's start with hydrochloric acid. So if you were to take hydrogen chloride gas and dissolve it in water, you make a solution called hydrochloric acid. That substance in solution will ionize, and so I'm using a different term here, ionize. Usually that term is for a substance that is not made of ions, like hydrogen chloride, that breaks apart into ions. So HCl is a molecular compound, yet when you put it in water, it produces ions in a process called ionization. So according to the Arrhenius definition, since hydrogen chloride gas produces H plus in solution, HCl is an acid. Let's take a look at sodium hydroxide. Sodium hydroxide is an ionic solid. So when in water, we say it dissociates, technically not ionize, though it's kind of the same thing. Both involve creating ions in solution. So for sodium hydroxide, because that substance produces hydroxide ions in solution, it is considered, according to the Arrhenius definition, a base. All right, a little different definition. We have Bronsted Lowry acids and bases. Again, we'll start with an acid. A Bronsted Lowry acid is a substance that donates a proton or a hydrogen ion. Isn't a hydrogen ion just a proton? Take a hydrogen atom, has one proton, one electron. Take off the electron to make a +1 ion, you're left with a proton. So probably easier to think of it as a hydrogen ion donor. So any substance that donates a hydrogen ion to something else is an acid, according to the Bronsted Lowry definition. Well, it's got to donate that hydrogen ion somewhere. It donates it to another substance. That substance that accepts that hydrogen ion is a base, according to the Bronsted Lowry definition. Take a look on page 576. So if you take ammonia and put it in water, what happens is a hydrogen ion, an H plus, from the water molecule is transferred to the ammonia molecule, and you end up producing ammonium, NH4 plus, and OH minus. So this kind of fits both definitions. You produce hydroxide ions in solution. We have a proton being donated by one substance and accepted by another. In this case, since the ammonia is accepting a hydrogen ion, it is a base according to the Bronsted Lowry definition. And surprisingly, water I thought was neither acidic nor basic, can act as an acid. It is doing so here. It is donating a proton to the ammonia molecule. If you take a look on the previous page, 575, we have a table of some substances and conjugate acids. We have bases and their conjugate acids. We'll talk more about the relationship between a substance and its conjugate. And you can probably kind of see there, if you compare, say, acetate to acetic acid, ammonia to ammonium, carbonates to hydrogen carbonate, and so on. Actually, we're going to jump ahead a little bit because it's going to ask for it in this question. Going back to that table, what is the relationship between acetates and acetic acid? And what is the relationship between ammonia and ammonium and all the rest there? So what we see is that these substances that we're comparing differ by one H plus. When two substances differ by one H plus, we call them a conjugate pair. More specifically, they're known as a conjugate acid-base pair. So here's how it works. The acid has one less or one more H plus than the base? Take a look in that table and see if you can answer that question. Well, we can see that the conjugate acid has one more H plus than the base, or conversely, the base has one less H plus than the acid. All right, so let's do some practice with that. Turn to page 576 and go ahead and do practice problem number 2. Both A and B we'll just do here is fine. It says, what is the conjugate base of each of the following? Go ahead and pause the video and answer that question, those questions. All right, so conjugate pairs are substances that differ by one H plus. So I've wrote both. A substance that has one more versus one less H plus than, in this case, H2SO3 in letter A. So again, make sure you understand, what is a base? How does a base compare to an acid? A base has one less H plus than an acid. So the conjugate base of H2SO3 is HSO3 minus. Now notice I didn't just take off a hydrogen, I took off an H plus. So take off an H and reduce the charge by 1. So we went from 0 to -1, HSO3 minus. Same thing with H2CO3. Again, we have two options here, one that has one more H plus, one that has one less. The base is the one that has one less H plus. We get HCO3 minus. All right, let's take a look at some more examples. I'm going to have you do a little bit more with this situation. I'll do one for you, and then you can do one on your own. So let's take a look at this equation. We'll talk about later why this is an equilibrium equation. And here's what I want you to do. We have a reversible reaction. We have in each reaction, the forward and reverse, one acid and one base. What we're going to do first is to identify the conjugate pairs, and we're going to kind of link them together with a line. And we're going to identify each substance then as an acid or base. This is, of course, according to the Bronsted Lowry definition. So let's start with CO3 -2. Which substance differs from that by 1 H plus? Well, that, of course, is HCO3. Whoops, I forgot a sign there. HCO3 negative. So those are conjugate pairs. What differs from H2O by 1 H plus? That, of course, would be OH minus. So I'm going to link those two together. And then what is CO3 -2? Is that an acid or a base according to the Bronsted Lowry definition? Well, what is happening to the CO3 -2? It is gaining an H plus to make HCO3 minus. So it is a hydrogen ion acceptor that makes this a base. Now, something to be aware of too is that a substance has to have hydrogen in order for it to be an acid. So there's no way CO3 -2 can be an acid. It has no hydrogen to donate. So it can only accept an H plus. Now, if CO3 -2 is a base, then its conjugate must be an acid. And we can see that in the reverse reaction, the HCO3 negative is donating a proton to OH minus, and because of that is turning into CO3 -2. Now, as I mentioned before, cannot have something donating a proton without something else accepting a proton. So if CO3 -2 is acting as a base, then the H2O is an acid. It's a proton donor. And if H2O is an acid, then its conjugate is a base. All right, let me give you one to try on your own. So let's go ahead and do this. Let's see if my pen will work. All right, so recopy this equation, and just like I did in the previous example, identify the conjugate acid-base pairs, and identify each substance as an acid or a base. Go ahead and pause and do that now. All right, so what we always want to do is we want to compare the substance to what it forms in the reaction. So HSO3, what happens to it? Well, it turns into H2SO3. So what must happen to HSO3 minus to form H2SO3? It must gain an H plus. So that makes HSO3 minus a base. If it's a base, its conjugate then is an acid. So H2SO3 is an acid. HSO4 minus, what is it doing? Well, it is donating a proton to the HSO3 minus, and such is becoming SO4 negative 2. So that makes HSO4 minus an acid, and its conjugate is a base. All right, we actually have one more definition of acids and bases. It is the Lewis definition. Be careful here. An acid, according to this definition, is an electron pair this time. So remember, it was hydrogen ion or proton for the Bronsted Lowry definition. Lewis definition has to do with electron pairs. An acid is an electron pair acceptor. And of course, then a base must be an electron pair donor. Now, in order for a substance to behave as an acid according to the Lewis definition, the substance must have an empty orbital in its valence shell, something that it can use to accept a pair of electrons. Likewise, to behave as a base according to the Lewis definition, the substance must have a lone pair of electrons, a pair of electrons that is not sharing with another atom, that it can use to donate to another substance. So let's take a look at an example. Reaction between BF3, boron trifluoride, and ammonia. So let's do this. Let's go ahead and draw Lewis structures for BF3 and NH3 kind of close to each other. We're going to write kind of a chemical equation for this process using Lewis structures. So go ahead and draw those Lewis structures, pause the video, and I'll show you what happens. All right, so what is the hybridization of the boron in boron trifluoride? Notice I didn't put the lone pairs. I could, I guess. I'll put them on there to make a complete Lewis structure. So what is the hybridization of the central atom in BF3? So we have a trigonal planar molecule. Hybridization is sp2. That means it has one unhybridized p orbital in its valence shell, an empty orbital that it can use to accept a pair of electrons. In fact, when you mix these chemicals together, that pair of electrons, a lone pair of electrons on the nitrogen in the ammonia molecule, is donated to the boron. And that pair of electrons is actually used to make a covalent bond between the boron and the nitrogen. So let's draw the structural formula for the product. So now the boron and nitrogen are bonded to each other. And so we end up with a molecule that looks like that. So again, this pair of electrons came from here. There's actually a name for this situation where the bond forms when one atom or molecule donates both electrons to the pair. Usually it's one electron from one atom, one electron from another, and they share that pair of electrons. In this case is different. The name of this bond is known as a coordinate covalent bond, or the IBO likes to call it a dative bond. So either way is fine. So it's just a covalent bond that forms when one atom donates both electrons to the pair. I'm going to skip this section for now. If I determine that it's important for us to go over now, especially in preparation for maybe IB chemistry, we can do that later. So we're going to skip it for now. So jump ahead to right here, acid nomenclature. So maybe you've heard names of some acids. I've named some acids. We've used some acids in our experiments. And so how do we name acids? Well, it depends. There's a different naming system for binary acids as there is ternary acids. So prefix bi means two. So a binary acid contains two elements, one of those being hydrogen and the other is some nonmetal atom. So here's the example I want you to think of. We've used this in at least one experiment, maybe more, actually more. What is the name of HCl when it's dissolved in water to form an acid? Okay, well, let's take a look at the naming system here. The names of all binary acids, all of them, start with the prefix hydro, and then we take the second element stem, so it's not the whole name, so this is not hydrochlorine. So we take chlorine, take the end off, and just have chlor, and then they end in ic acid. So the name of HCl is hydrochloric acid. Take a look on page 578. We have some names. I'm going to go over some of these and I'll give you some others. Let's take a look at examples. We already did HCl. How about the name of HF? Go ahead and name that. HF would be called hydrofluoric acid. How about HBr? That is hydrobromic acid. HI? Hydroiotic or hydroiodic, depending how if you say iodine or iodine. Either way is fine. Hydroiodic acid. And how about this one? Now, don't be caught off by the fact that there's two hydrogens here in this one and only one in the other. Doesn't matter. We're still going to name it the same way. Start with the prefix hydro. This one's a little bit different because we're not going to use just the stem of the second element. It's not hydrosulfuric acid. It's going to be this time the whole name of the second element. So this is called hydrosulfuric acid. So that's two words. Hydrosulfuric, one word. Second word, acid. So that is how we name binary acids. All right, ternary acids, also known as oxoacids, contain three elements. They contain, of course, hydrogen and then some oxygen-containing polyatomic ion. So here's how it works. Let me ask you this. If you ate an acid, what would it taste like? I'm not talking about the burning sensation. I'm talking about sour. If you ate an acid, it would taste icky. So I'm trying to help you remember something here. 8 ions make ic acids. So if the polyatomic ion ends in 8, then the end of the name of the acid is ic acid. Likewise, ite ions make us acids, O-U-S. So let's take a look at some examples. So we have HNO2. So what is the polyatomic ion? Again, this is a molecular compound. This is a molecule, so there's technically not a polyatomic ion in here. But if you put this in water, it would ionize to produce a polyatomic ion. So what is the polyatomic ion in this acid? Well, NO3 minus is called nitrate. NO2 minus, that has one less oxygen. If it has one less oxygen, it's going to have the ite suffix. So NO2 minus is called nitrite. HNO2 is called nitrous acid. How about H2SO3? Again, don't worry about that there's two hydrogens. Doesn't matter. Be careful. This is not hydro anything. This is a ternary acid. SO3 negative 2, what is that called? That is called sulfite. So what is the name of H2SO3? That is sulfurous acid. So take off the ites from sulfites. And this one's a little different because it's not just sulfus, but sulfurous acid. All right, let me give you another one to do. Go ahead and pause the video and name that. All right, did you get nitric acid? NO3 minus is called nitrate, so HNO3 nitric acid. All right, go ahead once again, pause the video and name that acid. Did you come up with sulfuric acid? So SO3 negative 2 is called sulfate, kind of like with sulfurous acid. We're going to take sulfuric acid. Be careful with sulfuric acid and what we saw on the previous page, hydrosulfuric acid. One of them is binary and the other is ternary. All right, couple more. Go ahead and name that. CO3 negative 2 is called carbonates. H2CO3 is called carbonic acid. One more, name H3PO4. Again, this one's a little bit different. It's not phosphic acid, but phosphoric acid. So there's not a straight relationship between the name of the polyatomic ion and the acid, but hopefully you get the idea. So be familiar with these. Later on, towards the end of the year, we will learn about another class of acids known as organic acids. So that'll be much later in the year. So remember when I said that some acids are excellent conductors of electricity and some are so-so? Same thing with bases. Well, that has to do with this here, the strength of an acid or base. So by definition, an acid or base is considered strong if that substance ionizes completely in water, meaning all of what you put in water breaks apart into ions. If that's the case where that substance is producing a lot of ions in solution, it's going to be an excellent conductor of electricity. So strong acids and strong bases are strong electrolytes. They are excellent conductors of electricity. Sometimes we have acids and bases that do not ionize completely. We call them weak. So they only moderately ionize or partially ionize in water. Coincidentally, these substances, weak acids and weak bases, establish dynamic equilibrium with its ionized and unionized forms. So again, when we write the ionization equation for a strong acid or strong base, what goes here? It's going to be a one-way arrow. By the way, when we write the ionization equation for a strong acid, we can write it one of two ways. This is one way. On the next slide, I'll show you another way. As for weak acids and weak bases, let me give you an example. Acetic acid is a weak acid. A solution of acetic acid is a so-so conductor of electricity. Why is that so? Well, because acetic acid, when you put it in water, does not ionize completely. Only some of it breaks apart into ions, and some of it remains as unionized acetic acid molecules. So that's how we write their different equations. Just know that the more ions that are produced in solution, the better that substance is at conducting electricity. All right, I don't have a demonstration for you to show. Maybe I'll try to put that together later, but I wanted to show again how we write the ionization equations for strong acids and bases versus weak acids and bases. So I showed this on the previous slide. When writing the ionization equation for an acid, you can write it one of two ways, with water in the equation or without. So if you put water in the equation, what goes on the right side is not H plus, but rather H3O plus. So there's the ionization equation for hydrochloric acid showing the complete ionization. All of it breaks apart into ions. I'll write a similar equation for acetic acid, again showing the water in the equation. It is not a strong acid, and so we're going to write the equation with this double arrow equilibrium equation. Again, we get not H plus, but H3O plus, along with acetate ions. All right, so you might be thinking, okay, how do we know if an acid or base is strong or weak? Well, pretty simple. You memorize all of the strong acids and all of the strong bases. So for the acids, there's three strong binary acids. They are hydrochloric acid, hydrobromic acid, and hydroiodic acid. And then for the ternary acids, technically we can use this. Any ternary acid where the number of oxygens in the compound exceeds the number of hydrogen atoms by 2 or more is a strong acid. So the strong ones you need to know, the ones we mostly encounter, are sulfuric acid, nitric acid, ClO3 minus is called chlorate. So what is HClO3 called? It's called chloric acid. And then we have ClO4 minus is called perchlorate. So what is HClO4 called? That is called perchloric acid. Oops, I should have put those under examples. Sorry about that. So there are the strong acids. Memorize those as soon as possible. Strong bases. All of the group 1 hydroxides are strong bases. This, of course, does not include hydrogen hydroxide. So lithium hydroxide, sodium hydroxide, potassium hydroxide, and so on. And then some of the heavier group 2 hydroxides, starting with calcium. So calcium hydroxide, barium hydroxide, and strontium hydroxide. Now notice the group 2 hydroxides have 2 OHs for every cation, of course, because the cation has a +2 charge, where the group 1 hydroxide is just a 1-to-1 ratio in this case. So anything besides those that are listed here can be considered to be weak unless you are told otherwise. All right, some more on weak acids and weak bases. Again, these substances only partially or moderately ionize and therefore establish dynamic equilibrium when dissolved in water. As we've seen, equations for these substances dissolving should be shown as equilibrium equations. We have a double arrow showing that it is not completely ionized. So let's look at a couple more examples. We mentioned earlier this one, nitrous acid. Be careful. Nitrous is weak. Nitric is strong. So when we write the ionization equation for nitrous acid, we're going to use a double arrow. We get H3O plus and NO2 minus. Here's an example of a weak base. Ammonia is a weak base. In fact, many nitrogen-containing compounds are weak bases. Now, when you write the ionization equation for a weak base, you have to include water. So for acids, strong or weak, the water in the equation is optional. Strong bases, no water, it's just a dissociation equation. Weak bases, you must have water. Ammonia does not completely ionize, and we produce in solution ammonium ions and hydroxide ions. All right, we've already talked about conjugate pairs, but here it is officially in the notes. I'll go ahead and fill that in. So let's go back and label this equation, the conjugate pairs. Label each substance as an acid or a base according to the Bronsted Lowry definition. Go ahead and pause the video and do that now. I just went with abbreviation here, A for acid, B for base. There are conjugate pairs, and there are each substance is labeled as an acid or a base. Now, do you notice something about the water? Water in one equation is acting as an acid, and in the other equation it's acting as a base. Any substance that can either donate or accept a proton is called amphiprotic or amphiprotic. So water in those last two examples demonstrates that there are other substances that can do that as well. All right, a couple more examples. Let's do this. Let's write the balance equation for the reaction between hydrofluoric acid. So remember that is HF and ammonia. And then identify the conjugate acid base pairs. And then I'll show you how to answer that next question. Go ahead and pause the video and do that now. There we have it all labeled. This next question, notice what it says here. We have two bases. F minus is a base and NH3 is a base. And we also have two acids. So both HF and NH4 plus are acids. So what it says here is HF is a stronger acid than NH4 plus. Now what does that mean? We're not talking about the degree at which it ionizes. We're talking about the extent that that substance can donate a proton. So really what this is saying is HF is better at donating a proton than NH4 plus. Now remember, we have all of these substances, all four of them present in solution at the same time. So HF is more likely to donate a proton than NH4+. So that means that the products are favored. The forward reaction is favored, the products are favored. You're going to have more products form than you will have reactants at equilibrium. So that's how that works. All right, let's try one more. Go ahead and do this one on your own, both parts. So write the balance equation for the reaction between hypochlorous acid, HClO, and ammonia. Identify conjugate acid-base pairs. Identify each substance as an acid or a base. And then answer that question there at the bottom. Go ahead and pause and do that now, please. So again, what is this telling you? NH3 is better at accepting a proton than ClO minus is. Because of that, that means once again the products are favored. So it's always going to be the side opposite of where the stronger acid or stronger base is located. So the forward reaction is favored because this is a stronger base than this, and we're going to have more products at equilibrium than reactants. All right, this concludes this very long lesson. Thanks for hanging in there.